So today we're going to get into special segments. So again, we're working with circles and we're going to learn about different relationships that have to do with different segments in circles. And we'll see a lot of terms that we've seen before, but basically just a quick review of the different types of line segments that we can see when it comes to circles. Basically, we can see a chord. Just a reminder that chords run from both ends on the circle, so both of its endpoints will be located on the circle. So in this example, we have two chords. We have A to F and B to H. So basically, a chord contains two endpoints that run on the outer part of the circle. So the endpoints extend from one side of the circle to the other side. We also have what are known as segments. A segment is it crosses the circle in 2 points with one endpoint on the circle and the other endpoint outside of the circle. So basically, it runs through the circle. So in this example, our segment is B to G. So one of its endpoints will be on the circle and the other one will be on the outside. In this instance, the one on the outside is the G and the one on the circle is B. That's a segment. Next thing, tangent. A tangent runs on the outside of the circle. It intersects the circle at exactly 1 point, but it typically runs on the outside. So in this instance, our tangent will be from C to E. And as you can see, it intersects the circle at exactly 1 point, which is this point right here. And that point is actually known as our point of tangency. Is the point of intersection between a circle and a tangent. So that would be our point of tangency. D is our point of tangency. So that's chord, secant, tangent, and then tangent gives you your point of tangency. Okay. Any questions about these definitions or what a chord is, what a secant is, or a tangent? All right. So now we're going to see how these different types of segments relate to each other whenever they are in a circle. So we're going to look at, I think, a total of 3 different theorems, which are pretty straightforward. So here we have intersecting chords theorem. Basically, this says if 2 chords intersect inside a circle, then the product of the lengths of the segments of one chord is equal to the products of the lengths of the segments of the other chord. So basically, product references multiplication. So basically, if I add, or I'll show you in color because it's a little difficult. Okay, so we have 2 chords, right? We have 2 chords because the endpoints run on the outside of the circle. So let's look at this chord right here. Basically, what this is saying is that if you take the length of HK and you take the length of AG and you multiply them together, that should be equal to the length of J to K multiplied by K to I. And we'll see an example of this. But basically, we have 2 chords intersecting at the center of a circle, like we do here. We're inside the circle. Then you can take the product of both of the parts of one side of the chord and both of the parts of the other side of the chord, and they should be equal to each other. So we'll look at that right now. So here's an example of that. Okay, so this says circle 0 is known to have the following segment lengths or segment lengths. So I'll just write this in. A to E is 5, C to E is 6, and D to E is 4. Well, what our intersecting chords theorem basically tells us is that we can take the length from A to E and multiply it of the length from E to C, and that should be equal to the length of B to E times the length of E to D. So that is what the intersecting chords theorem tells us. Okay, and so now we can plug in the different values we have. We know that A to E is 5, A to C is 6, B to E is, we don't know, and E to D is 4. So basically, we're asked to find the missing length of B to E. So I'll just plug this in so we can see it a little better. We're looking for the length of BE. So 35 times 6 is 30. How do we isolate BE? Well, we divide by 4, which tells us that BE is equal to 30 divided by 4, which is 7.5. Okay. So using the intersecting chords theorem, what we're able to do is solve for the missing part of the chord, given the relationships between these two chords when they intersect with each other. Okay, any questions about this? Questions, concerns? And so both parts of one chord will be located on one part of the equation, and then both parts of the other chord will be on the other side of the equation. And basically those two should be equal to each other. Okay. So here's just another example where we don't necessarily have values, but we have equations, but we can still use this to solve. So let's find x. So we're still going to use the intersecting chords theorem. So that basically means that if I take NK and multiply by the other half of that chord, KL, that should be equal to OK multiplied by KM. Right? So I have both of my chords in their parts on one half and the other one on the other side. So I'm multiplying those together. Now I just plug in what I'm given. I'm given that NK is equal to X. KL is equal to 15. Is equal to OK is equal to X plus 1. And KM is equal to 10. So now I can solve for X. How exactly do I do that? Well, this is 15X. Here I have to distribute. So that gives me 10X plus 10. Okay, now I'm going to isolate X. How exactly do I do that? Minus 10X gives me 5X equals 10. Divide by 5 on both sides. X is equal to 2. Now I know that X is equal to 2. Can I solve for O to M? Well, O to M actually runs from one endpoint to the other endpoint. So basically what I want to do is add those two parts together, this part and this part together, to find the entirety. So O to M is equal to K plus 1 plus 10, because I need to add those two parts together. I'm adding my OK part plus my KM part. And now I know what X is. It's just 2, so I can plug that in. So 2 plus 1 is 2, which gives me 3 plus 10, which gives me 13, which tells me that OM is equal to 13. Okay. Any questions about this? Questions, concerns? So basically, this theorem just tells me that I can take the parts of one side of my chord, or one of my chords, take the parts of the other side of my chords, multiply those parts together on both sides, and they should be equal to each other. Okay. Now we have this secants and segments theorem. And this one says, if two secant segments share the same endpoint outside of the circle, so that endpoint has to be outside of the circle, then the product of the length of one secant segment and the length of its external segment equals the product of the length of the other secant segment and the length of its external segment. That sounds like a mouthful. So basically what it's saying is if I have two secants, remember that secants have one endpoint on the circle and the other one on the outside. If those two secants share a common endpoint, which is going to be this one, then what I can basically do is the same thing which I did for chords, and that is that I can take this part of this secant and multiply it by this part of this segment, and that should be equal to this part of this segment multiplied by this part of the secant. Okay, so that is what we see here. UX is our blue part. Actually, hold on. My mistake. Kind of the same, a little bit different. So I should have looked at the equation. Okay, a little bit different from chords in that what you're actually going to do is going to take U to X and multiply it by the entirety of the segment. So U to X and multiply it by the entire length. So U to V. You'll take here U to Y and multiply that by the entire segment. So that's how it's different, that you have to take the entire segment, W to U, and you multiply those together and they have to be equal to each other. So U to X multiplied by UV should be equal to U to Y multiplied by U to W. Okay. So it's a little bit different, but kind of the same. And the difference is that instead of multiplying it by a part and a part, you're multiplying it by a part and the whole. Okay. And so I'll show you exactly what this looks like here. It says if second segments J, K, and JI intersect at point J, find the value of X. So we know here that we have two seconds that share a common endpoint. This would be my common endpoint. So that means that I can use the seconds and segments theorem. Okay. And basically the seconds and segments theorem tells me that I can take this part and multiply by its whole, and then that should be equal to this part multiplied by its whole. Okay, so basically, JL multiplied by JI should be equal to JM multiplied by the entire second JK. So those should be equal to each other. Okay, so now I'm asked to find X. So let's go ahead and do that. Do I know anything about JL? Well, yes, I know JL is equal to 4. Do I know anything about JI? Well, J from I would be this entire length. So that means I have to add 18 plus 4. I need the entire length is equal to JM, which is 6, times JK, which is this entire length. This means I need to add those together. So X plus 6. Okay, so now I can simplify 4 times 22 is equal to, and I can go ahead and distribute this. 6x plus 36. 22 times 4 is 88 is equal to 6x plus 36. Am I able to solve for x? Well, yes, I am. I just need to isolate x. So minus 36 gives me 52 plus 6x divided by 6 divided by 6. I can't simplify that any further, so x is just equal to 52 divided by 6. Okay, because if I were to actually divide it, I would get a long decimal. Don't necessarily want to work with that. So I'm able to solve for x here, which is what I need to do. Okay. Any questions about this? Questions, concerns? So basically, our intersecting chords theorem allowed us to take the parts of one chord, multiply those together, and those should be equal to the parts of the other chord. Okay. Well, our seconds and segments theorem basically says we can take one part of our second, multiply it by the whole second, and that should be equal to one part of the other second multiplied by the entire other segment. Second. Okay, and so that's the difference between the two. And so we're going to look at one last, oh, we actually have two other theorems, but this other theorem, And this theorem just basically says seconds and tangents segments theorem. So basically, if a secant segment and a tangent segment share an endpoint outside of the circle, so that endpoint has to be outside of the circle, then the product of the length of the secant segment and the length of its external segment equals the square of the length of the tangent segment. Okay? Sounds like a mouthful, but it's pretty straightforward. Basically, if we have a tangent, remember that a tangent runs on the outside. So this would be our tangent. It runs on the outside of the circle and intersects it only at one point. So that means this would be our tangent. If that tangent and our secant share a common endpoint, which is this one right here, then we can use this theorem, the secant and tangent segment theorem, to solve for any missing length. So this would be my secant. And so basically what it's saying is that I can square the entire distance of my tangent. So a to z squared. And that should be equal to the measure of the part of my secant. Come on, pen. That should be equal to, it's not writing. Hold on, guys. Read it right. Hold on, let me stop sharing and then share again. I just need this thing to connect. Oh. All right now. So you can't. Okay, let me share back. Sorry about that. Okay. So basically, I can take the entire distance of my tangent and square it, and that should be equal to the parts of my secant multiplied by the entire length of my secant. Okay, so that's what this is saying. So b to z was the entire length of my secant, and c to z is my part of my secant. So that's what it's telling me. Okay. So say I have a problem that looks like this, and this looks a little complicated, and it basically says, but it's super easy. It basically says, suppose a satellite is flying 151 miles above Earth's surface. The diameter of Earth is about 792 miles. He is a point on the surface of the Earth such that GH forms a tangent segment with the circle representing it. What is the distance from the satellite to point H? Okay, well, basically what this is telling us is that we have a tangent and a secant, and they share a common endpoint. And so given that, are we able to find what is the distance from the satellite to point H? Okay, so what is our tangent? Our tangent here is H to G. This is our tangent because it runs on the outside of the circle and it intersects it only at one point. And then we have a secant, which is this one right here, from G to E. And we know that we can use the secant and tangent segment theorem because they share a common endpoint, which is my endpoint G. Okay. So given that information, I should be able to solve what is the distance from the satellite to point H. So what is the difference from the satellite to point H? So more specifically, what is the distance of my tangent, right? Because that was my tangent. So what I want to do is use the relationship between the secant and tangent that I know. I know that part of my secant multiplied by the entire distance of my secant needs to be equal to the entire distance of my tangent squared. So that's my tangent squared Now let me take my part of my secant, e to g, and that needs to be multiplied by my entire secant, so e to g. And by doing so, I should be able to find the distance of my tangent, which is g to h, okay? So e to g, what is e to g? Well, that's this entire distance, and what I'll notice is that I have to add this plus this to find the entire distance. So 7,926 plus 151 multiplied by d to g. D to g is just 151. Should be equal to gh, which is just x squared. Okay, so I need to solve for x. So by doing that, I can simplify. Give me 1 second. Oh, 1 second. Hold on, guys. Okay. So basically, I need to get rid of my x squared, so I can square root, which tells me that x is equal to 1,104.4. Okay, so I'm able to solve for the length of my tangent using the relationships between the secant and tangent segment here. Okay, any questions about that? Okay, and then last theorem we're going to look at is the two tangents theorem. This basically says two segments, tangents to a circle, form a common external point are congruent. So basically, if I have two tangents, so here's my first tangent, and I know it's a tangent because it runs on the outside of the circle and only intersects it at one point. So this is my tangent. If I have one tangent and another tangent that share a common endpoint, well, then those two tangents must be congruent to each other. So that would mean that GH is congruent or equal to JH, which is pretty straightforward. If those two tangents share a common endpoint, well, then they must be congruent to each other. Okay, any questions? And so like this, we're able to identify what congruent line segments can be identified on the triangle with the inscribed circle. So basically, if we're using the two tangents theorem, we're looking for all the tangents which share a common endpoint. Here we have a common endpoint. Here we have a common endpoint. Here we have a common endpoint. And so because we have multiple tangents that have a common endpoint, we could say that this tangent and this tangent are congruent to each other because they share that common endpoint A. This tangent and this tangent are congruent to each other because they share that common endpoint B. And lastly, this tangent and this tangent are congruent to each other because they share that common endpoint C, according to the two tangents theorem. If you have two tangents that share a common endpoint, then they're congruent. All right, any questions about this? Okay. So what did we review today? Well, we looked at different types of segments that we can have when it comes to circles, chords, segments, and tangents. And based on that, we have different types of properties that we can use to find missing line segments measures. The first one was our two chords. If we have two chords that intersect, then what that tells us is we can take the parts of each chord. So we could take this part, multiply it by this part, and multiply it by this part, and those should equal each other. So JK times KI should be equal to G to K multiplied by K to H. That's basically what we got out of that first relationship. Okay. okay? The next relationship we looked at was two seconds that share a common endpoint. And basically what we learned from that is we can take one part of a second, so u to x, and multiply that by the entire length of that segment, so u b to u, and that should be equal to my other second, the part of its second, y to u, and that should be equal to the product of w to u. So that's how we got that relationship. Next thing, we looked at the relationship between seconds and tangents. Basically, here we have our tangent, a to z. The length of the tangent squared should be equal to the part of my tangent multiplied by the entire length of my second. That. And then lastly, if I have two tangents that share a common endpoint, then those have to be congruent to each other. So G to H is congruent to J to H. Any questions about what we looked at here? And we'll go through some practice problems on Tuesday. But does anyone have any questions right now? Okay. If there's no other questions, you guys may log off, and I will see you guys tomorrow. Not tomorrow, Monday. Bye, guys. Bye, Joelle.